are, Chapter 10. Let's take a look at the exercises for this week. Question number 1. For each of the following hypotheses, create a chart that shows the 4 possible outcomes that could occur as a result of hypothesis testing. There should be 2 correct decisions and 2 incorrect decisions. Label the type of error for each of the incorrect decisions. Okay, so we're going to do a little box here. Let's do truth over here. So if the truth is that we reject, or that the null hypothesis is true, which means that there really is no effect. The alternative hypothesis is true, means that there is an effect. Our 2 outcomes up here from our study, do not reject the null hypothesis, or we could reject the null hypothesis. Now, if we choose not to reject the null hypothesis when the null hypothesis is true, we've made a correct decision. If we reject the null hypothesis when the null hypothesis is true, then we have made an error. If we do not reject the null hypothesis when the alternative hypothesis is true, we've made an error. And if we reject the null when the alternative is true, we are correct. So here's our setup. Now the question is, what types of errors do we have? Type 1 error is when we conclude that a independent variable has an effect when it does not. So this is a type 1 error. And a type 2 error is when we do not reject the null hypothesis when we should. Okay, so let's look at these scenarios and see if we can write up something about the decisions. A new reading program in the elementary school is hypothesized to improve reading comprehension. So, the null hypothesis for A is no effect on comprehension scores. And B would be reading comprehension improves for our alternative hypothesis. So let's look at this setup for our 2 types of errors. A type 1 error, if we reject the null hypothesis when in fact the null hypothesis is true, we're saying that the program increases or improves reading, but really not. So that's a type 1 error. We are saying that there is an effect when in reality there is no effect. A type 2 error is the opposite. We will say program does not improve reading, but it does. So let's take a look at at B, people who take at least 2 vacations each year are happier on average than people who do not take at least 2 vacations per year. So a type 1 error, vacations improve happiness. That's what we'll say, but in reality it does not. Which is actually my point of view. I don't have fun on vacations because vacations are work, especially with kids. Type 2 error, vacations we conclude that vacations don't improve happiness, but actually they really do. Here, let's do the college student one. We could insert pretty much any stimulant in place of caffeine. Maybe an Addy, something. Okay, bring my box back. So type 1 error. A college student cramming for finals hypothesizes that caffeine improves the ability to concentrate. So if we reject the null hypothesis and we say caffeine helps, but really not. Our type 2 error is when we say caffeine doesn't help, but it really does. So that's how we can understand our type 1 versus our type 2 errors. Number 3. If we fail to reject the null hypothesis, but should have rejected it, what type of error have we made? Well, that's a type 2 error. Right? We should have rejected it, but we didn't. That's a type 2 error. Why is it type 2? This is how I remember. Type 1 is the worst kind of error. A type 1 error says something has an effect, like cures cancer, when in reality it really doesn't. Type 2 error means that you've missed an effect. A drug cures cancer, but you said that it didn't. That's how I remember the difference. Type 1 is the worst. Type 1 is the guilty man being Type 1 error is the worst outcome. The innocent man being treated as if he's guilty and executed. That's worse than having a guilty person go free. 5. For each of the situations below, describe what would be considered a type 1 and a type 2 error. So, a political scientist compares older and younger adults' attitudes towards the death penalty. So if we're looking at age, a type 1 error says that there is an effect when there isn't. So we could say that older adults approve of the death penalty more than younger adults. So we found an effect, but there is really no difference between the two groups. That's a type 1 error. A type 2 error there is no difference in support for the death penalty between age groups, but there really is. An age gap. Type 1 error says there's an effect when there is no effect. So for B, a movie critic wants to know if people prefer to see movies in 3D or not 3D. Is there a difference in preference for 3D movies versus non-3D movies? A type 1 error says people prefer 3D movies, but they really don't. Type 2 error says people don't prefer 3D movies, but they really do. C, type 1 error, people care about the name brand difference. People can taste a difference in name brand cereal over generic cereal, but they really can't. Type 2 error is people can't taste the difference between generic and name brand cereal, but they really can. D, the teacher wants to know if boys and girls differ in their career goals. Again, type 1 error says there's an effect when there is no effect. Gender, boys and girls, have different career goals, but they really don't. Type 2 error, there's no difference between boys and girls in their career goals, but there really is. Okay, let's look at number 7. Below are two hypothetical situations. We have a study A, which has two groups of equal size, and study B, two groups equal size. Okay, calculate the standard error of the difference and the t-test for independent means for each study. Standard error of the difference. This is standard error of the difference of the means. S1 squared divided by N1 plus S2 squared divided by N2. Okay, so for study A, let's do study A on this side, where I'll plug our numbers in. S1 is 2.5. We're going to have to square that and divide that by 20 plus 3.25 squared divided by 20. Take the square root of that. Let me grab my calculator. Okay. You've seen me do lots of math. I'm just going to go ahead and plug the whole thing into my calculator. Take the square root, second function, square root. This is equal to, let's do the rounding correctly, 0.92. Okay, we got to do t. T is equal to x1 minus x2 divided by 0.92. x1 is 14.50 minus x2 is 12.75. minus 12.75 equals 1.75 divided by my standard error of the difference, which was 0.92. T equals 1.902. 1.90. Okay. We have to do this for the other side. So we'll get the square root of, now we're on to study B. For the B side, we have the same numbers, 2.5 squared divided by, 65. Use the calculator. So what happened? The only thing that's different between study A and study B are the sample sizes. So if we look at N1, it's 20, N1 in study B is 65. So we've increased our sample size by 45. What happened? Well, larger sample size here in the denominator made these fractions smaller, right? You increase the size of the denominator, the value of the fraction decreases, so our standard error also decreased, went from 0.92 to 0.51. Oh, I forgot to calculate t. T for this is 14.5 minus 12.75 divided by 0.51. T equals 3.43. How does increasing the sample size affect the calculated values of the standard error of the difference? Well, we already figured that out. Makes the standard error get smaller, and the t statistic gets bigger, because if your denominator gets smaller, then the value of your fraction increases. How does increasing the sample size affect the probability of making a type 2 error? Type 2 error, when we say that there's no effect when there really is. This is an example of type 2 error. This is a pretty small t. When you have a small number of observations, you are likely to not reject the null hypothesis. But with a t of 3.43, we should have rejected the null hypothesis. So this is an example of a type 2 error. Increasing the sample size decreases the probability of making a type 2 error. That's what we want. Question 9. Two researchers separately testing the same hypothesis end up with the same sample size and standard deviations for the two groups. However, the experimental manipulation is more effective for the second researcher, which results in a bigger difference between the means of the two groups, as well as, calculate the standard error of the difference. Well, the first thing to check is that our sample size are equal, and we know that. So the standard error of the difference is equal to the square root, and let's see, S1 squared divided by N1 plus S2 squared divided by N2. Alright, let's see if I can shorten this up. Okay, so let's do it for the first researcher. Let's double check. Oh, well, this is going to be the same because they have the same sample size. S1 is 0.5 squared divided by 12 plus 0.75 squared divided by 12 square root. Grab my calculator. And so for the first study, this is 0.26. We'll have to do t for the first study. Now the difference between the two groups, x1 is 2.50 minus 2.15 divided by 0.26. Grab my calculator. 2.5 minus 2.15 divided by 0.26. T is equal to 1.346. So let's call that 1. Sorry, I'm questioning myself. Why isn't that right? Okay, 1.34, only 0.35. So that was for our first one. For the second one, the only difference between the second researcher and the first researcher are the values that they get for X. Right? Because the two researchers have the same sample size and they have the same standard deviations. So this is going to be the same. But the second researcher had a greater difference between the means of the two groups, which is going to be evident in our t-scores. 2.70 minus 1.95 divided by 0.26. So let's go ahead and test that out. 2.7 minus 1.95 is 0.75 divided by 0.26. My t is going to be equal to 2.88. Does the increased in-between group variability affect the calculated value of the t-statistic? Well, yeah, right? So what we're doing is we're changing what's in the numerator, right? We're changing what's the size of the difference. So that's greater between group variability. Does that change the t-statistic? Yes, absolutely. Does that as well change the probability of making a type 2 error? Actually, yeah. It reduces the probability of making a type 2 error. Because remember, type 2 error is you find no effect when there really is one. Right, so the type 2 error decreases. 11. Two research studies compare two groups on the same dependent variable. Both studies are based on the same sample size, and somehow both studies end up with the same means for the two groups. However, in collecting her data, the second researcher provides clearer instructions to the research participants. As a result, the scores in the second study are less influenced by random chance factors. The standard deviations for the two groups looks like they decrease from the first study to the second study. All right, calculate the standard error of the difference and the t-test. I already know how this is going to go after the last two. So let's go ahead and just do it. For the first study, start with the standard error. And yeah, I got this memorized. S1, okay. So here's S1 is 11.23 divided by, my n is 17. Don't forget the squares. I'm going to go ahead and just calculate this out. .79. T is equal to the difference. So what was our mean difference? It was 77.62 for x1 minus 68.05 for x2. T equals 3.19. Okay. Let's do this for the second study. Now remember, with the second study, what changes? What changes in the second study is our S's, and our values of S are going to go down. square root. And the square root is 3.10. Same difference between the two groups. Now we have a smaller standard error. What's going to happen to t? Well, we got a smaller denominator. Stupid calculator. Clear. 77.62 minus 68.05 equals, oops, you forgot the decimal point. 99% of the mistakes I make are me typing numbers into a calculator. Okay. So what happened? That's a very good question. Remember how I said most of my mistakes are from typing into the calculator? Pretty sure I just made another one. Yeah, I did. Sorry for that. Okay, so what happened after I fixed my calculator mistake? We have a difference in the t-scores between the two groups. How does decreased within group variability affect the calculated value of the t-statistic? Well, it actually increases the t-statistic as well as the probability of making a type 2 error. We're actually reducing the probability of a type 2 error. Okay. Type 2 error is when you mistakenly, possibly, do not reject a null hypothesis when you should have rejected a null hypothesis. So you say that there's no effect when there actually is an effect. A higher t-score is saying it's more likely that there's an effect. All right, this is a huge one. I'm going to walk through this rather than doing all of this. And it's one of those questions where it uses a previous question. So let's think about this together. A researcher wishes to test a drug that claims to improve memory. The researcher sets up an experiment where a control group receives a placebo, like a sugar pill, and an experimental group receives the memory pill. So that's our independent variable, whether or not you've received the pill or not. The following data are the number of sentences each participant correctly recalls after listening to a 2-paragraph story. So you read a story, and then you have to repeat it back. The researcher in exercise 12 notices the large amount of variability within each of the two groups. Large amount of variability, some people get most of the sentences, some people get none of the sentences. There's a wide spread. Investigating why, the research assistants counting the number of correctly remembered sentences differed in what they counted as a correct sentence. So we don't have the same measurement. We're measuring them differently. Some experimenters counted them as correct if the participant remembered the idea of the sentence, whereas others only counted it as correct if every single word was recalled in the correct order. This is bad science. When I do content analysis and have multiple people coding, there's a statistic I have to generate known as an intercoder reliability score. So basically I have to make sure that person A and person B, if given the same object to code, are coding it the same. To decrease this source of error, he redid the experiment, handed out instructions on what should be counted as correct. What you should have done in the first place is train your coders. Using the new data and the steps of the hypothesis testing, determine if there's a significant difference between the groups. Okay, and this time they give us the raw data. Right? They give us the numbers for the placebo and the numbers for the experimental group. And now we're flashing back to chapter 3 where we have to come up with the mean and the Chapter 4 with the standard deviation. We state the null and the alternative hypothesis. The null hypothesis says that the mean of group 1 is equal to the mean of group 2. The null hypothesis says the mean of the placebo group is not the same as the mean of the treatment group. Calculate degrees of freedom, set alpha, alpha is 0.05, stated decision rule, so we have to draw our curve and say where it is that the shaded region of T is. Calculate the t-test for independent means, reject the null hypothesis. Yeah, I'm not going to do all of that. I'm not going to sit here and watch you make you guys watch me add 7 and 4 and 5 and 6 and 5 and 7 and 6. I'm not going to do all that. I will, however, show you how that I would do this really quickly. If I didn't have a lot of time, I would just throw these in an Excel file. And so you can see over here that we have the placebo group and the experimental group. That's not what I wanted. Fun little Excel fact that when you highlight multiple cells like that, it actually gives you the average right down here and the number. So my n is 7. The sum of the 7 numbers is 52, and the average of the cells that I select is 7.43. So that's what I would do. And then to calculate the standard deviation, if you just start you can make Excel do calculations by hitting the equal sign, and then there's probably a million functions you can use. This one is STDEV, which is standard deviation, .s for sample. So I want the sample standard deviation of, and then you tell it which numbers to select. That's the quickest way to go ahead and get these numbers. I know I've taught you to do it by hand, but sometimes, again, when you're in a hurry, you don't want to make a stupid mistake with the calculator like I do most of the time. Just go ahead and put them in the numbers in Excel. Can't do that on a test, but we could do that on a homework. So if we went through and we did all of this, we have 12 degrees of freedom, because n minus 1 plus n minus 1, so 7 minus 1 is 6, 6 plus 6 is 12. The critical value for t with 12 degrees of freedom is 2.179, so as long as we're above or below 2.179, we will reject the null hypothesis. Going ahead and calculating the t-score, we get a standard error of the mean difference. You can go ahead and do this, hit pause, and then come back. 0.71. Our t-score is going to be the difference between x1 and the mean of x2, and that is negative 2.42. So we are out here in our little curve, so we would reject the null hypothesis. So what are we saying? We're saying that there's an effect, that the drug is making you more likely to be able to recall this paragraph than those who took the placebo. So what happened? Well, we made an error. We made specifically a type 2 error. We rejected the null hypothesis, or we failed to reject the null hypothesis when we should have. Why? Because there was a lot of group variability. And when you reduce in-group variability, you also reduce the chances of making that error. I'm going to stop there. The other exercises in the chapter are things that we don't really use all that often, and I'd rather you take the remaining time, extra time from this shorter video this week on working on your papers. So that is type 1 and type 2 errors. You are all now experts at this. This should be second hat. You'll also notice that doing a hypothesis test is easy for us now. We know the process of setting up alpha, calculating degrees of freedom. You should be comfortable with difference of means testing in all sorts of situations. And hopefully you will experience less type 1 errors than type 2 errors, because the type 1 error is the really bad one. Again, you find a significant relationship when you should not have. You should have not rejected the null hypothesis. A type 2 error is when you think you have no findings, but in reality you do. So you think you wasted all that hard work and effort doing an analysis, and it turns out that you just didn't find it, probably because your sample was too small or the method you used was too sloppy. So that's why we really don't want to throw away observations. We want to make sure that we use as many observations as possible. Keep our N really high. All right, that's it. Go work on your papers. Thanks.